Okay, it's my pleasure to introduce Dr. David Tarboton from the Utah State University. David is the principal investigator on HydroShare, what I see as Quasi 2.0, as it would be, but I know they're doing some more interesting things as well. So without any other ado, David?
Well, thank you. I appreciate the invitation to talk. I've enjoyed being here, learning about CyberGIS, and I'll look forward to telling you a bit about HydroShare. There's actually a fair bit in common. We are both SSI projects, so I'm interested in also listening and learning and hearing your suggestions and sort of addressing your questions. Answering the tough question we're all striving to address, I guess that Mike posed yesterday about what is the science that's enabled by the software that could not otherwise be done. So let's see if I need this. Yeah. So here's my outline. I'll first talk a bit about the quasi-hydrologic information system, which is where this work has started. It's essentially a service-oriented architecture-based system for sharing hydrologic data. Then I'll move into talking about HydroShare, which is the web-based collaborative environment we're working on now for extending the data types that we are able to work with, and also including models. And then I'll bring some connections into CyberGIS, where I'll talk about the hydrologic terrain analysis work that I've done, the TAUDEM software we've heard mentioned a few times, and touch on some of the ideas for river geometry, which is one of the ideas that we're working on in HydroShare. So there's a number of challenges we face dealing with hydrologic data, really related to heterogeneity. We have data from many dispersed sources, sometimes different federal agencies, different investigators who've collected data for different purposes. So it's in all sorts of different formats. And often the easy questions in science related to hydrology that perhaps deal with single data sources have been addressed, and the way we're going to actually make progress in understanding is by integrating information from multiple sources. So that's going to be one of the themes that I'm going to try and highlight, and that's at some level the problem that we're trying to address is also data integration. At the beginning of the Quasi-HIS project, we did a user survey or a need survey and asked what proportion of your research time do you spend on pre-processing data into the appropriate form before you can sort of get started with your research. And we found a lot of people actually spend a lot of time. The large majority of the respondents said sort of 10 to 25%. Some people said 25 to 50%. Some people even said 50 to 75%. So that's quite a lot. Thankfully, nobody actually responded more than 75%. So there's a lot of time spent accessing the data, working with it. Another problem that I think is important is this issue of a digital divide. I think the capabilities that most of our researchers, most of our graduate students have, I've sort of depicted on the left there, people who go out into the field and sometimes collect data, and believe it or not, that's me in a few younger years. Working with perhaps visual programming, that's an ArcGIS model builder sequence, and on laptops. And then there's the sort of big data and high performance computing, where some of the stuff we saw yesterday, where you get under the command line and it really gets pretty geeky and intimidating in dealing with job submittal codes and the sort of stuff that we need to sort of help people through. So the question I think that's important is how can we best structure data and computer models to enable the use of high performance data intensive computing by disciplined scientists who do not want or need to learn the ability to deal with the sort of, I'm going to say, arcane language of supercomputers. And that's what we need in terms of gateways, web interfaces, and I think CyberGIS is helping with that. And we'd also like to help with that with HydroShare. So I've mentioned COHASI a number of times. That's the Consortium of Universities for the Advancement of Hydrologic Science Incorporated. It's essentially a universities consortium founded to provide community research support services to advance water research. Most of the major universities in the US are members, and it has a number of activities, one of which is effectively cyber infrastructure and hydrologic information systems. So over the last several years, there's been a team under the auspices of Quasi developing the hydrologic information system, essentially as an internet-based system to support sharing hydrologic data. So it's got servers connected through web services as well as software for data publication. And this slide sort of mashes up the three elements of it. HydroServer is the platform for publishing data. So if you have an experimental watershed or a group that you wanted to share data, you would establish a HydroServer. It's based on a database that runs on Microsoft SQL, and then it's got Esri ArcGIS server for serving maps. Then there's the catalog, which is at San Diego Supercomputer Center. That's effectively the centralized location where there's that supports data discovery. So there's keyword-based search as well as geographic search for data. Then there's the desktop client, which is for data access, and that's based on an open source GIS, the sort of dot spatial system, and then it's sort of Hydro Desktop is the name given for that. And that's the emphasis again is combining multiple data sources. So there we've got an illustration of data from Lake Powell storage and inflow. The storage data comes from the Bureau of Reclamation. The inflow data comes from the USGS. So it uses effectively a services-oriented paradigm, which is similar to the way the web works. So we might think of web servers people established to initially to start publishing data on the web, and then you needed a browser to access them. And in the early days of the web, we all maintained long lists of bookmarks, and we sort of shared good websites that had useful information. A lot of that has fallen by the wayside with the large sort of cataloging systems that are effectively Google and Bing, and that crawl all the web pages on, and then provide capability to search for them. So HIS follows a fairly similar paradigm in that HydroServer you establish to effectively make your data available. So it's a distributed or federated system. Then HydroCatalog is a centralized place that supports discovery, and once you register a server at HydroCatalog, then the metadata services will effectively harvest the data and or harvest the metadata so that it can support the search. And then Hydro Desktop first goes to the catalog to help discover data, and then it retrieves the data from the original source. So one of the concepts was leave the data with the person responsible for collecting it. They wanted to sort of keep possession of it. That paradigm is changing a little bit because we're finding people actually don't want to bother with that, and they want to find a way to have somebody else take care of it. So Quasi now has a water data center that's happy to take over your HydroServer data if you're done with it. There's standards that make all of this happen, and one of the sort of success stories is shepherding this concept of WaterML, a markup language for exchanging hydrologic time series data through the Open Geospatial Consortium standardization process to effectively get the uptake of big organizations such as USGS, World Meteorological Organization, as well as companies like Kistas that are in the sort of big players in the water data world. So this sort of gives a bit of a illustration of some of what the problem is trying to be addressed. It used to be that you had to sort of have a lot of expertise in where you would acquire data from, and you'd have to go and get data from one location, say the USGS, another location, say the EPA. You'd need to, and this is the problem of people spending a lot of time getting data from different sources in different formats, and playing the role of integrators. So what HIS enables is effectively a generic search request and a generic sort of get values request that can retrieve data from multiple sources. So now if I'd been bold, I would have actually run a live demo of this, but since I'm working on the systems computer and not my laptop, and we don't have Hydro Desktop installed, you'll have to bear with these slides. But I've got a couple of slides that just illustrate what Hydro Desktop does. So when you open it, it's a map-based open source GIS. It's getting, so in this case you can see the Esri Hydro base map as the sort of background layer. So it's using standard map products to sort of give you context. You can zoom in on a location, and here I've zoomed in on my hometown of Logan. Then you click to delineate a watershed. So here it's consuming web services that are actually supported by EPA for delineating watersheds. And then you can use some of the GIS functionality to sort of put a buffer around that and say search for all of the data in that domain of interest in the last 22 years. And you get a lot of data returned. You pick the sites that you're interested and perhaps download and plot the data. So here I identified there a SNOTEL site that has snow water equivalent data that's from the NRCS, and I downloaded a USGS site that is stream flow in the Logan River. And you can see there's a sort of a correlation there. So you might be interested in, so what, I want to study this a little bit more. One of the capabilities you'll notice on the tab there's Hydro R. So there's a capability to effectively interoperate with R, and you can open the R window that really just provides a very light interface to read from the Hydro Desktop database into the R environment, and then you have at your fingertips the sort of full analysis capability of R, and you can perhaps plot the data from multiple sources, the maximum snow water equivalent versus the maximum stream flow, and make your interpretation. So it's brought together data from multiple sources, distributed cloud resources perhaps, and the interoperability with a system like R enables you to there's hundreds if not thousands of R libraries that you could then work with this data with. What Quasi-HIS has given us is effectively a common window on water observations for the United States, unlike any that's existed before. Sort of storage in a community data model, publication from a server, data access through sort of internet-based services, tools for access and analysis, discovery from the sort of thematic and geographic search. I didn't really show that, but in the Hydro Desktop interface you could sort of put in keywords to filter out the data you want to discover. And then integrated modeling and analysis, combining information, in this case in the R environment. There's also a capability to connect models together using OpenMI, which is a model exchange system. So now I want to move on to talk a bit about HydroShare, which is the sort of new project. I should really acknowledge that all the work with the Quasi-HIS was a project led by David Maidment. I was part of the team, but he was really driving that. HydroShare is the sort of SSI project that's started up. It's fairly similar in scope to CyberGIS, except we've just been at it for 1 year, and you're coming to the end of your third year, so we're sort of lagging behind a little bit. And it's to support collaborative data sharing, data publication, and modeling. So we've set up a website, and we're really trying to sort of address the questions: can sharing of data and models be as easy as sharing photos on Facebook or videos on YouTube? One of the challenges with HIS is it's actually quite hard to publish data in the system. It's very good at getting data out of the system, say USGS data or EPA data or experimental watershed data, but you can't just casually say, I'm going to send you a data set, just like my daughter can send me a YouTube. Or can finding data and models be as easy as shopping on Amazon? Can I sort of put the filters to say, I'm looking for such and such an author about such and such a subject? So we're trying to sort of bring some of the sort of social media aspects to it, but focusing on the sort of hydrology value added. Currently, you can actually go to this website and work with it. It's a beta, and I've put the beta in big bold red because it's still got a lot of issues with it. But our first release is due in November. So it's to be a web-based system for advancing model and data sharing. One of the things we want to do is actually with Hydro Desktop, let that serve as a client so that you could be doing an analysis and sort of push your data back to the system. Somebody else could then retrieve it. Work with additional data types. And this is where using standards and having completely described data in terms of metadata is important. The catalog functionality would need to get expanded once you go into different data types. We would like to think of a model as just a sort of special type of data, perhaps. It's an object that you can share and you can describe and discover and reuse. Once you are starting to share models, if they're properly described, the step to then run them on a high-performance computing system shouldn't be that large a leap. And then focusing on the sort of social media collaboration functionality, and then trying to link to other data systems, recognizing the sort of importance of interoperability. So this is some screenshots of the website as it currently is. So you can go to the sort of My Content tab, and at the point that I was making this slide, there were sort of two resources. So we're thinking of everything in HydroShare as a resource, and as a consequence, the data model for describing resources is actually a fairly important part of our design. What content do we need to have to describe a resource? So here we've got a stream network delineated from a DEM, as well as the discharge in the Logan River. And then when you sort of drill in on a resource, you get a visualization of it. So this shows perhaps a visualization of the Logan River discharge, and I picked a period when there happened to be a fairly large flow. 2011 was the last year we had any decent snow there. And then one can write comments on it. So here I've got a comment. This time series shows the 2011 flood in the Logan River. Notice how much higher it is than the peak flows previously. And then to sort of encourage discussion, sort of +1ing the comments to give it ratings and things like that. Then hopefully simple upload capabilities. Right now we're only really supporting sort of time series resources, geoanalytics resources, which are sort of any geospatial format that can be visualized by this geoanalytics toolset that Renzi's built. And then we've got the sort of catch-all other, which if you have a data format that doesn't match what's there, you can still load it, but then there won't be any visualization or tools that works with it. So this is our sort of wish list of where we want to go with the resource types and some of the functionality. So time series, geographic feature sets, and other. Then things like what I call referenced time series, where we don't actually hold the data, but you create a reference to something else. A web server somewhere else that has the data, and you can just sort of discover it. Rasters, multidimensional space-time sets, river geometry, and you can read the list. And then for each resource, we'd like uploaders, viewers, exporters, best practice tools for sort of hydrologic data pre-processing and analysis. So now this is a bit of a sequence of some of our sort of vision for where this is going to go. So it's imagine the possibilities. Right now you can have instruments observe data, stream it into a Hydro server, and then you can discover and analyze it from Hydro Desktop. But that's where the current HIS ends. And what we'd like to be able to do is then take a result, push it back to the HydroShare resource store, enable access for a number of collaborators that can then sort of collaborate on the analysis, iteratively refining it, perhaps preparing a paper. Then that paper would get reviewed. This is the sort of picture of the Journal of Congress. And ultimately you'd publish the paper with the data, methods, and workflow along with the sort of description, and that would probably be in collaboration with systems like Data One and EarthCube that are dealing with those sort of things. In the area of modeling, we would like to establish links to data sets that models need, like the essential terrestrial variables that Chris Duffy sometimes talks about with his HydroTour, NASA's Earth Exchange system that has a lot of NASA remote sensing data, in which Larry Band, who's on our team, is working with Raman Amani and sort of trying to facilitate access to tools to pre-process and configure inputs. So here I've got TowerDem, and I sort of added the idea perhaps CyberGIS might have tools that are useful here. Sort of pre-configured models and modeling systems that may run as services. So if somebody is interested in running a model, a lot of time running models is actually spent just sort of configuring and getting them all compiled, and can that be avoided by having the model in a server or a cloud system? And I guess when I use a cloud system, I sort of think of supercomputers as part of that, because they're out there at really a server or grid. The sort of technical details, I guess I'm being loose with the technical details. It's important for standards to be used. So there's standards for information exchange, things like OpenMI, CSDMS has their basic model interface. I mentioned that briefly yesterday. Tools for visualization. If we're working with data in standard formats, there can be common tools, and a modeler can not have to worry about the visualization tools. And then I put in this concept, automated reasoning to couple models based on purpose, context, data, and resources. So I had a PhD student, Aaron Bird, and this is the image from him. And he's trying to construct a reasoning capability that will help identify what inputs a model needs, which is the most appropriate model to run given the question that you're trying to address and the information you have available. So one of the ideas is that with HydroShare being a repository for resources, you can sort of adopt this resource-centric paradigm for your work. So you might have the models that can interact with the resource, and the modeler just focuses on that, not having to worry about the visualization tools. Because those are there, and somebody who was working on visualization tools or analysis tools doesn't necessarily need, or those can be applied to all of the information in the repository, data loaders, data discovery tools. So multiple models to use the sort of common best practices tools available as a community resource, and we like the system to have it so that people can contribute information. One example is the SWOT model. It's fairly widely used in hydrology, and on our team is Venkatesh Marwade, who's at Purdue, and he's developed a system, Water Hub, which was based on Hub Zero, and it's effectively a system for running SWOT on the web, and now that's coming into HydroShare. So this expands out on sort of some of the details of dealing with a model. There was a lot in this sort of blue arrow here. You need to think of the pre-processing that's needed to get from the resource repository to the input files. Then the model would produce output files that perhaps have to go through post-processing. So some of that, I guess the process of connecting a model to the system is going to have to involve addressing this functionality. Now, ultimately, you might need to get, to the extent that the models can follow the standard formats, that might be fairly simple. But a lot of models, this is actually a non-trivial step. So this just gives a real sort of high-level view of our architecture. The interfaces being the web browser and the Hydro desktop. We're effectively using Drupal as the sort of foundation system to work with. So Drupal is a fairly widely used content management system. We adopted it because it's sort of well established. It's got a large community, a lot of modules to work with. The geoanalytics framework for visualizing and working with geospatial data. Then at the back end, there's iRods, which is the system that Renzi's working with. Actually, it originally had a lot of emphasis at San Diego Supercomputer Center, effectively for rules for sharing data, federating data, actions that can be done on data based on sort of microservices that would then sort of deal with things like indexing, data grid computation. So this just hits a few of the points about Drupal. It's extensible open source content management system. You can effectively theme it to give the look that you want, and use a lot of off-the-shelf modules, so we can focus on the value added, and really sort of only develop the custom modules that we need. So this summarizes the sort of HydroShare part. Collaborative website for sharing of hydrologic data and models, to expand quasi-HIS with additional data classes, models, scripts, tools, and workflows, focusing on community participation, interoperability standards, and open development. How much time do I have left?
You have 12 minutes, yeah.
Okay.
If you want, no questions.
So
10 minutes.
I wanted to talk a bit about Towdem, because a lot of people were touching on it or mentioning it yesterday. And I think Towdem, we would like it to be one of the tools that HydroShare can work with. Towdem is essentially the software that I've developed over several years for doing stream and watershed delineation and deriving useful information from digital elevation models for hydrologic analysis. And I think this also provides a good opportunity for interaction with CyberGIS. So it's a fairly extensive tool set. Some of its sort of unique capabilities are we represent the flow field using multiple flow directions, so water can go not only from one grid cell to one neighbor, but get shared between multiple neighbors. Lately, we've worked on developing a parallel implementation of it using MPI. It's architected so that all of the computation is in sort of open source platform independent C++ command line executables. But then there's a deployment as an ArcGIS toolbox that really just uses Python scripts to construct the command line to run it. And we've got a CSDMS implementation, and then I'm also working with some of the folks here on an Exceed implementation. So one of the things that we've sort of faced in the digital elevation model business is we started out in the 80s with 100 cells per square kilometer, and now with LiDAR, we can have 1 million cells per square kilometer. So that requires a fair bit of processing. Now, computers have gotten faster as well, but we've also seen the sort of plateauing of clock speeds and the need to go to parallel methods. So one of the fundamental ideas is topography defines watersheds, which are the basic hydrologic landscape element. So here I've shown a sort of a watershed, and delineating that is important. And here's a photo I took on the way in this morning that says Puget Sound starts here. So the notion, we're in a watershed, and if you're protecting your water, you sort of need to know where the watershed is. The nation is spending a large amount of money on elevation data for floodplain mapping. We know from what's happened in Boulder the last week or so that it's critically important. So we need to work with digital elevation models. The starting point is a fairly simple data structure. Elevation values on a grid. Probably many of you are familiar with that, although probably some are not. I guess all the people who deal with health and all the people who deal with community work, perhaps. But anyway, elevations. Think of a sort of a checkerboard like this floor, an elevation value at each grid cell, a sort of a dumb data structure. How can you get the richness of information required for hydrology out of that? So you need to go through a sequence of first getting rid of any pits or sinks that may be artificial, and often that's because of the process of digital elevation model creation, points that should drain somewhere that don't, then computing a flow field effectively representing which grid cell water from this grid cell would drain to, and then once you've got that flow field established, you can construct a whole lot of value-added information, where water would go, delineate streams, delineate watersheds, and the like. This just shows alternative ways of representing the flow field. You can have single flow directions, which may introduce some sort of a bias. You'd expect water to follow perpendicular to the contours, but in this model it may follow that sort of path. The alternative I proposed, which is this D infinity, splits the water between those two grid cells. So on average, it follows perpendicular to the contours, but at the cost of some spreading out that may not be always physically correct. So you've got a sort of a dispersion, numerical dispersion that's coming in. You can then do things like evaluate the contributing area, and this just sort of compares the sort of D8 contributing area, which has sort of stripes aligned with the grid directions, versus the D infinity approach that gives you a sort of smoother representation. That's a sort of visual evaluation. You can also evaluate it on sort of based on known surfaces and the errors to sort of quantify how good the algorithm is. But moving beyond just flow accumulation, I mean, flow accumulation is something you can do with ArcGIS as effectively an integration of a weighted function over a contributing area, which numerically is evaluated like this. But what if you want to have some sort of a different function? So generalizing it to the idea of what I call flow algebra, replace that summing of the weights by any general arbitrary function that operates on the flow directions, operates on input fields that are part of the result, and operates on independent input fields. And that allows you to do some sort of useful other things related to the flow field. And I've just given one example I'm calling transport limited accumulation. Maybe you have a grid that represents the supply of erosion material that perhaps you calculate based on slope. You have a transport capacity, which is perhaps related to slope and contributing area. Now you want to say how much sediment moves downslope, and maybe what's transported out of any grid cell is the supply or the transport capacity, whichever is the less. So you've got some sort of a threshold function in there. So building the capability to have thresholds or other sort of functions inside of the flow calculation is what I've called flow algebra, and it provides a general modeling framework for a lot of static flow field based geospatial concepts. So a lot of the functions in TAUDEM are actually constructed using this concept. The parallel approach, we took effectively a fairly naive idea, just dividing the domain into stripes and sending one off to each processor with a sort of a buffer to support communication. The logic of it is to try and construct everything in terms of queues so that when something is ready to be processed, it can be. So the first thing you do is find out how many grid cells drain into any grid cell and count that. Then look at all the grid cells that don't have anything draining into them. Those can immediately be evaluated. Now there's a long list of those. So those go on the processing queue. Then as you evaluate each grid cell, sort of moving over to the right, you evaluate the arbitrary flow algebra function. And when the queue isn't, so you process items off the queue, evaluating the function, then decrease the number of cells the result depends on. If it gets to 0, add it to the queue. Swap information across the buffers and repeat until you're done. So one can also string together functions to I guess we built a lot of the sort of foundational elements that can then get strung together to get all the products in sort of one fell swoop, if you want, and end up with a data structure of catchments that drain to channel links with sort of downstream and upstream connectivity represented. So I got the 2-minute warning, so I should probably skip over this. We've done some examination of sort of timings, scaling as you move from small to large. And this just gives a bit of a history of sort of starting out what we could do in 2008 in terms of this domain we could process to what we can do now. And then work that's ongoing with the Exceed team's Extended Collaboration Support Service to effectively sort of remove some of the bottlenecks that arise due to our naivety and some of the initial coding and make it more efficient. And then maybe so I guess one of the things, these are sort of pretty pictures that come from Open Topography, which is a system for publishing LiDAR data that's supported at San Diego Supercomputer Center. And you can get really high resolution digital elevation data, such as this. And then when you notice this little road here that you can actually see in the DEM, you can then calculate contributing area from D infinity, and you can see the contributing area sort of down to the valleys. You can see the effect of the road on it. Notice here's a little trail going up the mountains. And if you zoom in, you can actually see what the model's saying in terms of the flow, how it gets distorted by the presence of that trail. Assuming, of course, that water is flowing across the land surface based on the topographic flow directions. Now you may get a lot of it infiltrating, and maybe it's smoother than that. So we've got parallelization, speeding up processing, and sort of partition processing, reducing size limitations. You can sort of skim over those details. And maybe since I'm out of time, I'll just sort of skip to the end. So I've talked about the quasi-HIS's enhancing access to hydrologic data, HydroShare as a collaborative website for sharing of hydrologic data and models, and then TAUDEM, where there's opportunities for implementing in servers and clouds. And I skipped over this river geometry part, which is one of the parts of HydroShare. So there's a lot of people working on the HydroShare team. So there's a picture of some of them and some of their names. But I'm happy to answer questions if I left any time.
Thanks, David.